So as I explained to you before, for this time, we determined the poster award by the voting from all the participants, okay? Voting from you. And I will show the result, okay? This is determined by number of votes from the participant. And according to the just number of vote, we determined 8 winners. Okay, so let me pronounce. Daria Dall'Ollio, Thomas McGees, Elizabeth Borchardt, Nagayoshi Ohashi, and the eDisk team, Dominique Segura-Cox, and Joseph Varga, I'm sorry, maybe my pronunciation is not good, Iain Hammond, and Sarah Betty. Okay, could you go to the front, please? Ah, yes. So this is a very Japanese style, by the way. And this seat is also very Japanese. So let me read what is written on this. We call shoujo. It's a kind of a proof of the award. Okay. Best Poster Award is presented to Daria Dall'Ollio, okay, for the outstanding poster presentation entitled Magnetic Field Inside Out, Unveiling Magnetic Field in Massive Protostars at Protostars and Planet 7. Okay. Shu-ichiro Inutsuka, the PP7 organizer chair. Congratulations.
Thank you so much.
Yeah. So it takes time, so therefore now, from now I only say the name. So, okay, so congratulations, Tom McGees. Okay. Sorry. It's okay. Thomas. Okay, sorry. I'm not. Sorry, I didn't mention the order. Okay. Congratulations, Thomas McGees. Yes. Okay. Congratulations, Elizabeth Borchardt. Ohashi-san. Okay. Congratulations, Nagayoshi Ohashi and the eDisk team. Okay. Thank you. Dominique? Yes. Okay. Yes, please. Okay. Congratulations, Dominique Segura-Cox. Joseph? Okay. Congratulations, Joseph Varga.
Thank you very much.
Iain, yes. Congratulations, Iain Hammond. Sarah, okay. Finally, congratulations, Sarah Betty.
I am not Sarah Betty. I'm her supervisor. She's on the plane.
Okay. It's okay. Sarah, unfortunately, she's not here, and she's a supervisor, her supervisor. So, and actually yesterday, lunchtime, we had a SAC meeting. And in the SAC meeting, we discussed who will give a talk. And after some discussion, we have chosen 4 kind of young, early career people to give a talk. Well, those are these people. Okay. So now we'll have 12 minutes plus 3 minutes Q&A session. So in total, it's about 1 hour. So let's start the poster hour talk. Okay. First, Daria Dall'Ollio.
Can you hear? Yes. Well, good afternoon to everyone. It's my pleasure and my baby pleasure. She is Jaya. I'm a postdoc, the first postdoc of my life at the moment, at Chalmers University of Technology in Sweden and at the Osservatorio Astrofisico di Arcetri in Italy. So probably the font is not reproduced in this laptop, but well, it will be okay. Okay, so the topic of my study is trying to understand the role of magnetic field in massive star formation. I'm joining the two institutes in Italy and Chalmers, and we are trying to propose observations to figure out what is going on and what is the role played by magnetic field there. So she is really disappointed. Don't be disappointed. Okay. Let me try to. Sorry. Do you want to stay in this way? This way, maybe? No? Okay, let's go. Ciao. Ciao. Finally, I have some rest to my arms. So we are trying to understand what is going on, speaking at different, basically, wavelengths and basically different scales, from cloud to core scale and disk and outflow. So the main point is that we have seen during these beautiful reviews in the past days that magnetic field permeate the interstellar medium and also magnetic gigantic molecular clouds. And then during the collapse of the cores and during the formation of the denser region inside the clouds, the magnetic field lines are basically dragged by the material and they are distorted, and then they created these beautiful hourglass shapes. This is, of course, according to a magnetically regulated collapse, and eventually, due to the rotation of the disk, we can see that the models present this sort of spiral shaped lines that are basically twisted by the material that is rotating. So this is, of course, the theory. But when we go to look at the observation, we see that there are some works that are confirming and they are consistent with the observation, with the theory. So they are producing observations that are basically hourglass-shaped morphologies, while there are other works that instead are basically showing random morphologies. And yeah, this is of course a problem because we don't know what does it mean. So it's really true that magnetic field does have a role in the fragmentation of the cloud or not. We still have to work on it, and also we have to investigate if it's important for the cloud collapse, for the creation of the disk, of the accretion disk, and the launching jet process. So we think that having a multi-scale and a multi-wavelength approach can help a lot. And therefore, we decided to build a sort of sample of high-mass stars to observe. And we want to observe them starting from the larger scale of the cloud and moving to the smaller scale of the core, and then also inside the disk and the outflow system. So what we want to stress is that we have seen during the past meeting that there are several traces that can be used, like dust, polarization of dust. Chandrasekhar Fermi method was widely described, and we learned a lot. There is also another method that is called thermal line polarization, and it's given basically by the Godel-Khilafik effect. So we can study the polarization of the light coming from thermal line and see the magnetic field properties through this method. But I want to stress attention now on masers that we can consider very good tools to study magnetic field, especially at the small scale of the disk and the outflow. because we have several papers, and if you are curious, you can go to the beautiful review by Crutcher and Campbell recently published, and we can see that they have narrow beams, very strong beams, collimated, and so we can aim to look at the polarization of light, in particular the secular polarization, looking for the Dema splitting, and this is important because we can measure the magnetic field strength, right? And recently, there are observation versus simulation that I compared in my paper, studying basically methanol maser and see if it is really reliable, because there can be some non-Zeeman effect that can arise during the of course, the polarization production, and can affect the measurement of the magnetic field. So I try to understand if this non-Zeeman effect can really influence the observation, and I've seen that no. Luckily, all the methanol measures that we can observe, the transitions that we have observed until now, are all lying in the Zeeman regime. So all the contribution that we see is really due to the magnetic field and not to something else. Therefore, we can aim to use several maser species to look at different regions of the outflow and also different regions of the disk, depending on the process that we want to observe. Well, there is a nice work from Gabriele Surcis and the C7538, and they saw several maser species, methanol, OH, and water. Methanol was produced in the region of the disk, water in the outflow, and some OH masers in the disk as well. So they are tracing different regions and also different processes, and so we are facing different densities. But we can use them to have like a sort of landscape of the magnetic field across these small scales. And also, we can aim to trace the evolution of the magnetic field in time. Because if we look, for example, at water masers at different age, like for example in this case W75N observed in 2005 and observed in 2012, revealed a magnetic field morphology that was changed because there was the tip of the outflow that was pressing away the material. The shocked water basically produced water mesoid, and they revealed different polarization pattern and different magnetic field morphology. So merging all the things together, like trying to reach a sort of complete view of the magnetic field would be wonderful, especially if we can have the same source observed with different tracers. Like, for example, we are trying to do this work on IRAS 18089. We have new WLA data on 44 giga methanol measures that they are arriving. And then we have also thermal line polarization on the same source, trying to tracing the outflow. No, don't do that. It's too complicated. So this will be really interesting to see, because in this way we will have a 3 independence method altogether, and in particular we will see if the previous link that we mapped in the disk between the dust continuum in the disk and the 6.7 gigahertz methanol measure in the disk is preserved also in other method. Thank you. Yeah, so the last slide with the conclusion. Having these 3 methods together is an opportunity for the future. So I'm really looking forward new collaboration, because I think that it's time to merge the community working on dust and the community working on maser, also to produce like comparison and see if the results are matching. So we will increase, using the 3 methods together, the consistency of our results and also the reliability, because the methods are basically 3 different and they are independent. And then I want to thank you for voting my poster and for your attention. And I also want to thank deeply the LOC, because they helped me a lot with the baby, as you can see now. And you also know that one of the goals of the sustainable development that are set by the United Nations regards gender equality, the achievement of the equality, and the empowerment of women and girls. And we are just after the pandemic. And I have seen on my shoulders that there are a lot of problems in getting again in touch, and being able to participate to this meeting was a really great opportunity for me, even with the baby. So we felt really welcome, both me and my baby, and this is really a thing that doesn't happen always. So again, thank you again, Locke, for all the effort, and for Eb, because you did a great job. Thank you.
Thank you very much. We do have time for questions, so please, if you have questions for Segura, please come up, line up for the microphones.
Hello.
Ah, there's a question, sorry.
Hi, thank you, great talk, I love it. First of all, I'm writing I have a very similar idea, so we should totally collaborate. But my question is about the masers. So class 1, class 2 masers, methanol ones, and water as well. I don't think there is a consensus as to when they turn on, when they turn off in terms of evolutionary stage of the objects. So
yeah, you are right, because it's still under debate. So, but the point is that depending on the thing that you want to observe, of course, if you want to look at an object that is more evolved or not, you can use one or the other. One thing that happens is that methanol class 2 are always found thermally excited, so they are not related to shocked region, but something that is basically thermally emitted, while the class 1 is emitted when there are shocks. So maybe you want to use one on the other, depending on the fact that maybe you want to look at the outflow instead of the disk, for example. But definitely, we need more concerns, more observation to figure out exactly when as you said, when they are arising.
Yes, sorry, I forgot to say, my name is Tatiana Rodriguez from New Mexico Tech.
Yeah.
But yes, I think it's very important for us to work on maybe a high-resolution survey to try and trace also how intense these are in these regions, to try and determine if we can do circular polarization measurements, for example. So looking at these regions with different frequencies and all, to try and understand where they are and which ones, that'd be great. But
yeah.
I'll catch you later.
Yeah, absolutely.
Please.
Thank you so much.
Thank you.
So there's a second question, please.
Hi, Kate Pathwell, UCL. Beautiful results, thank you very much. So it's very interesting to see the thermal polarization, the Goldreich-Kailafis results. I think these are going to become very important in the next few years, now that ALMA's doing spectropolarimetry in a big way. Is there a possibility using the results? I know there's a lot of ambiguities on predicted magnetic field direction from Goldreich-Kailafis from models. Is there any possibility of calibrating those relationships with your data? I'm still working on the calibration. Those are preliminary results. So I have to say that before saying anything, I want to have 100% certainty that these are correct. So to model all the polarization and the effect, basically we have a code that is called Portal, and the Portal code was produced by Lankar et al. In 2020, and so all the details on these things are basically in this paper. So I will send you, if you are interested in these things, to this work. Amazing,
Okay.
Thank you very much.
Thank you.
So let's thank Dominique again. Thank you very much for a nice talk.
Thank you so much.
And then we move to the next presentation. the adapter. So this is given by Dominique Segura-Cox. Please go ahead.
Okay, that's straight. Okay, there we go. Okay, so I'm really glad that my title was a bit general because I have a lot of thoughts about streamers. So my whole point of my talk, if you're going to remember anything about my poster at all, is that it's just the title. Streamers feed embedded Class 0 and Class 1 disks when planets are just starting to form. Okay, so what's a streamer? So Rachel Friesen talked about this just a little bit in her review chapter, I think on Tuesday? It's a while ago now. But streamers are very simple to understand. They're just asymmetric funnels of material that dump material into disks or directly onto protostars from their larger scale environments. And we've seen them observationally and in simulations in both high and low mass protostars, and in really highly embedded Class 0 and 1 disks, or in the slightly older and slightly less embedded Class 2 phase. Basically, as long as there's anything surrounding a protostar or a disk, you will get a streamer. So my favorite streamer is the one that I'm finishing up my project on now, which is IRS-63. This is a very young Class 1 protostar in the Ophiuchus molecular cloud. And when we observe this, we see that we actually have this sort of envelope material here that's completely asymmetric, right? It's this long, stringy structure. And it definitely falls right outside of the outflow cavity if we look in the 12CO. So it's definitely envelope. It's highly asymmetric. It's nothing like we would think about when we think about a typical spherical envelope. And when we look in the velocity structure of this H13CO+ line, we can actually use we can model the infalling trajectory here with a streamer model that's based on Mendoza 2009, and it's basically a prescription of a Kasson-Ulrich-Moosman infalling velocity profile. So we're taking something that was originally meant for like a axisymmetric infall system, and we just peel it apart until we have one infalling trajectory. We can use all of our history of working with protostars and their symmetry to build up something that is asymmetric. We also see here that there's this smooth transition down into this Keplerian rotating disk. It's very clear here where you see the red and the blue shifted Doppler profile that this is the disk here. And we have some red-shifted emission, which slowly transitions and smoothly wraps behind the disk on the red-shifted side, and then transitions into the blue-shifted side of the disk as it comes around. And we call this area over here the impact zone. And it's also important to remember that this is a young ring disk. In fact, this is still the youngest known disk with multiple rings that we know of. I would love it if somebody found something younger, but so far we have multiple rings in a Class 1 system. We haven't quite found multiple symmetric rings in a Class 0 system yet, although maybe the eDisk team will update on that in the next talk. And we love rings, right, because we sort of have this chicken and egg problem when we're dealing with forming protoplanets, is how do you keep the dust when they start to grow larger into pebbles and boulders in the outer parts of the disk, or at least far enough away that we can get solar system-like planets. And one way of doing that is to introduce substructures, and you can create pressure bumps, which can rescue those dust particles from falling inwards into the protostar on timescales that are just so short that you won't really actually form a full planet. So whether there are rings here or not, or sorry, whether there are planets here or not, I'm not sure, but there are definitely rings. So either there's planets that are carving out those rings, or those rings might be a favorable environment where planets may soon form. So we're having this asymmetric feeding of material into the disk in a stage where planet formation is pretty favorable. It's really the beginning, the dawn of planet formation. And that's not the only example of young rings and streamers. So we also have, in a slightly older system, studied by Felipe Alves, you have this wonderful ring disk. There's a really large scale ring in that one. It's being fed by these two streamers. You can have multiple streamers. And even HL Tau, which started off this entire business of studying ring systems, was found to also have a streamer, not only by Gregoufi, but also by Iain and their team. Oh, and before I move on, I just want to say that work done by Alexandra Kunstinova, who's a Sagan Fellow at AMHU, has also simulation evidence where if you have anisotropic accretion or non-symmetric infall onto disks, you can actually help form rings and substructures and help spur planet formation from that, in that sense. So having these streamers help form rings has actually already been predicted by theory. We need to start working together as a team. And I've also found, using the N2H+ molecule, which is we typically think of as a cold gas tracer, that the streamer hits the disk on impact. Oh, sorry. We actually find that the streamer hits the disk on impact. So remember, the impact zone is over here because the streamer falls inwards and smoothly joins the disk on this side. Now, if we thought that most of the heating was only from the central heating from the central protostar, or from perhaps viscous heating in a smooth disk, we would expect this ring to be perfectly symmetric, but it's not. We're missing the cold gas tracer on the side where it impacts, meaning that side must be hotter. And that's the side where the streamer impacts. That's just a reminder, these are now plotted on the same size scale. So you can see truly that really it is where it joins is where we're missing that cold gas tracer. It's warmer there in that side of the disk. That means the streamer can change the temperature of the disk, which can change the chemistry and the composition and what types of molecules are there to be available to be accreted onto planets. And it's not only that streamers can heat the disk, there's also work by other people that show that streamers can actually shock on impact. I'm not an astrochemist, but whenever I talk to astrochemists and we talk about shocks, they get really excited, right? When I worked with people with FAUST, which I'm a collaborator on, the FAUST Alma Large program, whenever we start to talk about shocks, we get excited because you can start to break apart molecules, which means you can have molecules that are ready to be assembled into other more complex species. Shocks are exciting. I haven't proven that my disk, that my streamer is shocking on impact, but it's certainly heating, and it's something we need to follow up on. But they definitely can, and we've seen that in other systems, including HL Tau. Again, one of those most famous systems. Streamers are just really cool. There's a lot of implications here, and there's a lot of work done by a lot of people. And speaking of work done by a lot of people, these are all streamers that have been found on accident, and I'd just like to point out a few. Only this streamer and this streamer by Jane Huang have actually been found on purpose. Other than that, all of these other 8 streamers have been found on accident because those programs were designed with other goals in mind. They just happened to target the right molecules with the right sensitivity and the right size scale to be able to detect the streamers. And what I find also interesting is that, as we see over here, this is sphere, that's scattered light. So SU Auriga actually has a streamer that's detected in dust, and it's rather large scale. So not only are you replenishing a large amount of gas into these disks that are on the verge of planet formation, you're also repopulating with potentially small dust grains on like ISM-sized dust grains. So that's changing your composition of the disk. And it's not just the observers that have been seeing streamers for a long time. There's also been a very long history of streamers that have been seen in pretty much any simulation, whether it's MHD, non-ideal HD, you can have non-ideal MHD, there's zoom-in simulations, there's AMR simulations. Whatever flavor of simulation you have, it's rather easy to create a streamer. And it's not just the studies that have already been done. There were 2 posters at this conference specifically looking at how do you actually produce streamers. One could be a cloudlet capture model, where a cloudlet is falling towards a protostar, and then it's elongated by a drag force into something that we might confuse with a streamer structure. Maybe that's still a streamer. Or there's also the case where you can have dense cores that collide and produce these elongated streamer structures that are still infalling onto protostars. And then Nina Filipova, who is in my group at University of Texas at Austin, just managed to take StarForge simulations and create rather realistically sized disks in them. And StarForge is interesting because the box of StarForge that you start with is 10 parsec in size. It's massive, and yet you can go from 10 parsec all the way down to a few hundred AU disk in one simulation. So that's a great future for her. It's really cool, and I'm excited to see what she does with that. So considering all of these accident findings, we decided that we needed to move on and do a full survey to figure out some more of these properties, because these have been detected in a variety of molecular tracers. And we do that with the Prodigy survey through NOEMA. And that's a shared program between Paula Caselli and Thomas Henning. And I've been steering the Paula Caselli portion of the program, which is focused on Class 0 and Class 1 protostars. But I'm not doing it alone. I just want to take a moment to acknowledge my amazing team that's been helping me out. We're making awesome progress, including lots of amazing streamers that we've been finding. Our program's only 75% done. We have about 50% of the observations calibrated, and we're already finding a ton more streamers. And it doesn't take a lot of effort to be able to find them. And one thing that I think is really cool is that with Teresa's work, she's found that the mass accretion rate from disk to protostar is about an order of magnitude smaller than the mass accretion rate from the envelope to the disk. So there's more mass being loaded into the disk than is being accreted by the central protostar. Okay, so I want to be just a little interactive in my last moments. So could you raise your hand if you're interested in gravitational instabilities, or binaries, or companion formation? And keep it raised. Are you interested in variable accretion or luminous outbursts? And keep them raised, please. Are you interested in where mass in your filaments or fibers goes? Because we don't know where these things originate yet. And keep them raised, please. And are you interested in disk chemistry or disk temperature? Because we're dumping a lot of stuff into these disks. So if you're raising your hand, please keep streamers in mind. You don't have to work on them directly, but just remember they're a thing, and they might impact your results. And with that, thanks, and I'll just leave these reminders up. And just a quick reminder, please hire me, because I'm on the job market. Thank you.
So this was perfect timing for the presentation. I hope somebody hires you on the spot. I see people lining up. Please, go ahead.
Peter Wojtke from Graz, Austria. Very nice talk. Exciting observations. I'm just, at one point, is not so convincing to me, and that you say that the cold gas tracer is missing. I would be more happy if you maybe found in your next observation program a hot gas tracer, because then it's clear. But you know, normally if you have molecules and you excite them, why should it go away? It's rather than, you know, many things go away when you lower the temperature and then only a few remain, and these are the cold tracers. But is there any prospect maybe to go for some high excitation?
Excellent question, and I think there's already a hint of it. And if Eleonora Bianchi is here, can you wave if you're, hi. She had a recent paper out on this protostar here, which is SVS 13A, and she found in some sort of complex organic molecule, I don't remember what, probably related to methanol, just a little hint of something also along the streamer that's feeding this dusty spiral. So they exist, I just haven't gotten there, but other people have.
And then just by coincidence, I'm offering a postdoc position.
Thank you.
So I see the link. Another question on the right.
Hi, Rajika Kurawita from the Heidelberg Institute for Theoretical Studies. Thank you for showing my paper. I've been getting really excited about streamers because simulations have been trained for a long time, and then since like the last protostars and planets, we're observing them, which is super cool. I was wondering, you said you see some of these streamers like falling directly onto stars. Have you seen any objects that are considered outbursting that have streamers associated with them?
That would actually be SVS 13A. It just happens to be a super highly studied system. But if you look, I think in here we go. In Hizé 2019 and Freeman 2017, they actually did find evidence of a previous outburst. Oh wait, that's for a different protostar, but they also found it for SVS 13A. So there is a little bit of a link, but there's so much to do. Like, I need other people helping too.
Yeah, okay, cool, thanks.
We have time for a very last, very short question. Please keep it short.
Okay.
Yes, please.
Yeah, Nagayoshi Ohashi. So well, very interesting. And, we, eDisk also, as you said, found more streamers, including your source. So there are two questions. One is your case, I see the acceleration towards the center. And another question is how much is the accretion rate you estimated?
Yes, so in that case, I'll take us to this image. So yes, in this case, I do see that it starts out at cloud velocity and accelerates until it reaches the outer disk velocity. So at least in this case, yes, there is acceleration as we reach the disk. And for this mass accretion rate, because I am using H13CO+, I don't know if we're actually measuring the full mass reservoir, but for this protostar, I'm getting a mass accretion rate of about 0.3 times 10 to the minus 6 solar masses per year.
Okay, that's a very definite answer. Thank you very much. Thank you again for the discussion. We will move to the next talk, which is by Iain Hammond. So this will take us to the planets, back to the protoplanets, please.
Okay, good day everyone. So we've heard a lot in this conference about how difficult it is to directly image a protoplanet. We're the only sort of known real confirmed detections of PDS-70b and C. And in this talk, I want to talk to you, or hopefully convince you, why we think we've found another planet in HT 169142. My name is Iain Hammond. I'm a third-year PhD student at Monash University. I'm supervised by Valentin Christians and Daniel Price. And if you're wondering where we're located, yes, we're from down under in Australia. We're in Melbourne. We have a team of about 10 people or so working on protoplanetary disks, whether it be imaging, simulations, ALMA data, or flybys. So let's just jump straight into the science. This beautiful image of HT 169142 was released in 2017 in Polar et al. And what you're looking at is light scattered off small dust grains around the disk, captured with VLT sphere in J-band. And you can see that the small grains are sort of concentrated into two rings. There's one like quite close to the star, and then another one further out. And they're separated by this depleted region that's in between the two rings. And we see a similar thing with ALMA, so in 0.89 millimeter grains and in 1.3 millimeter grains, there's the same story. This beautiful ring separated by a gap and then another ring. So and we know in theory that a planet could carve such a gap. I will also point out, while I'm here in this image in scattered light, that there is a really small concentrated sort of blob of material inside the annular gap. Hopefully you can see that from the projector, which you need to remember for later. So about 2 years after the scattered light image came out, Raphael Graton published Sphere IFS and eDisk data. So looking at the near infrared for signatures of a planet that could be embedded in that annular gap. And they found that there was this signature that is circled in green that overlaps in the IFS data, so it's shorter wavelengths, and then in eDisk data in the K-band. And they sort of postulated this is like a tentative detection of what might be a planet in the gap, but it wasn't exactly clear at the time if that was actually real or not. On the simulation side, there's a beautiful work by Claudia Tocci in 2020 who modeled HD 169142 using Phantom, which is a smooth particle hydrodynamics code written by Daniel Price, and also made a sort of a forward model prediction using MC-FOST, which is a radiative transfer code written by Christoph Pant. And in this simulation, there's a 2.2 Jupiter mass planet in the gap, which has sort of caused these two ring structures. And there is also another planet closer to the star in order to make that inner ring. And another team who included circumplanetary disks also found that for face-on systems, we can actually leverage the light that is being scattered off the circumplanetary disk of the planet to help us detect it. So in this case, we're not necessarily detecting the thermal emission directly from the planet itself, but rather all the light that is scattered off the grains that are sort of enshrouding the planet. This also means that the spectrum of the planet will be more blue in this case. So finally, more recently, we heard a lot about detecting planets kinematically with ALMA, which is an amazing new field. So looking at HD 169142 with ALMA in 12 CO traces, if you subtract just a Keplerian rotation profile from the gas, you are left with this kinematic signature. Encircled in green, again, is that same blob that was detected back in 2019 by Raphael Graton. There was also this red, this large kinematic feature sort of to the north, which likely traces the vertical motions along the outer ring in the system. So this could indicate that there is some non-kinematic feature crossing the gap where that potential planet could be. So I came along, and sort of my interpretation of this was that we could have two planets in HD 169142, one that is quite close to the star that we've sort of yet to detect, and then another which has been carved in this annular gap. And one way of detecting it would have been to try to find evidence of the spiral wake that is left behind in the outer ring, which I've indicated with this black line. So I consulted the Sphere archive. I went back and reduced three data sets using angular differential imaging, which we heard about in chapter 17, and also spectral differential imaging. And so the two new data sets that I reduced, as well as the scattered light on the left, where there's one in the middle and there's one on the right. And then scattered light again, you can see the small concentrated scattered light in the annular gap. And what we saw in the new angular and spectral differential imaging reduction was the blob of compact emission was there again at the same radial separation, but it had actually moved. And then in 2019, so 2 years after that 2017 observation, it had moved again, which was sort of underlying evidence that we could be tracing a planet. We also detected the spiral wake to the east in here in both of the ASDI data sets, and along with this mounting evidence, we decided to say in our letter this was no longer a candidate planet. This is actually the detection of a forming protoplanet. We have orbital motion measured. We have gas kinematics. We have an outer spiral wake detected, and simulations can reproduce both the ALMA and the Sphere substructures. So what is really nice about this, and I want everyone to sort of take home, is that this was not new data. This was data that had been sitting on the archive for many years. The newest one is almost now 4 years old. We simply went back and just did a careful reduction of what was already there, knowing where a planet might potentially be. And we were able to find this planet 3 times. But this also means that there probably could be more planets out there that can still be detected in existing data without requesting new data. This could be on people's hard drives or laptops or clusters, and we just haven't found them yet. For the Keplerian motion, if you weren't convinced by the picture, for prediction for planet at 37 AU, around a 1.85 solar mass star, inclined at 13 degrees, a slight inclination. It follows basically perfectly predicted Keplerian motion, and I'm sure we'd all believe Kepler's third law. And if you like visuals, we also have a movie that a citizen scientist made, which sort of overlays all 4 of our reductions, so the scattered light making up most of the image, and then the 3 detections using this sphere instrument. And you can see the planet moving between 2015, 2017, and 2018. Oh, sorry, 2019, sorry. So what's next for this? Well, we need tighter constraints on the planet's orbit. Sphere sort of gets us like part of the way there, so we can actually measure motion. But if we really want to measure eccentricity, we will need to use VLTI gravity to really nail down whether the actual orbital motion of the planet. We also want to determine more of its physical characteristics. So we only have sort of a very narrow spectral range at the moment. It's sort of in the near infrared. We want to try to get this JWST MIRI at 10 micrometers, and also try to determine accretion signatures with VLT Eris. Since this planet is likely enshrouded in a significant amount of dust, this makes it very difficult to go after this with H-alpha because that's quite susceptible to extinction. And finally, deeper band 9 ALMA observations would make detecting the protoplanetary disk will be most favorable to detect the protoplanetary disk since it is mostly small grains. That's the end of my presentation. I'll take any questions.
Thank you. Exciting to have another beautiful example to play with. Other questions? Please line up behind the microphones. Yes, please.
Hi, Charles Law, CFA. Great talk and very beautiful data. I just wanted to ask about the mass estimate you have here. So is the new data consistent with the 2.2 Jupiter masses that you had from the modeling, or do you have sort of a revised mass estimate from this new observation?
So mass estimates are still quite hard. We can only really put some rough constraints on it just through the observational signatures. So like ALMA dust says it could be around 1 Jupiter mass, but then we can't make it too massive, or else you'll just get huge spiral arms everywhere. So you can't go above anything like 5 Jupiter mass. But because this is obviously shrouded in a huge amount of dust, we're not actually directly imaging we are directly imaging the planet, but not the actual, not really the planet itself. It's more the circumplanetary disk. So it's not well constrained, but I would say it's between 1 and 5 Jupiter mass.
Okay, thank you.
Okay, we go for another question here in the front.
Kate Follett, Amherst College. This is a super interesting result. Thanks for sharing. And it looks very compelling. I think there's something like 10 previous scattered light candidates in this disk, and I was just wondering, this looks much more compelling than any of them, but I'm just wondering if you could speak to where it is relative to that, and I was curious in particular in your ASDI images, whether the inner mask was a software mask or the coronagraph.
Yes, so the other claims for protoplanets in this system, which I believe was like mainly your question, were within the inner ring itself. So they were sort of searching for planets that could reside quite close to the star. These, like, sure, you can get orbital motion easier, but you can't really use a coronagraph for those observations. and also there's a lot of speckle noise there, so it can be very, very difficult to sort of go after those planets. They certainly aren't ruled out at all by our new result. I know that there is believed to be, it's actually this blob here has been suggested by a couple of other teams. I think it needs more data. There was also, I know Sebastian Pires has suggested that there could be some sort of mini Neptune planet in these outer rings. We also don't rule that out either. But obviously I can't like image that. The other one's easier. Yes.
Yeah, I guess. More planets to be discovered. Let's take one short final question from the right.
Yes, I'm Margot Leemker. I'm from Leiden Observatory, over here.
Yeah.
And I would like to point out that there is already high-resolution Band 9 data of this disk. So we didn't see any circumplanetary disks there. So I was wondering if that could already give you a little bit of a hint on how massive your disk is. And I'm also happy to talk to you after the session is finished.
Sure. I didn't catch the first part of your question.
So there is already high-resolution Band 9 data of this disk.
Yeah.
And we didn't see any circumplanetary disks there. So could that already give you a hint on how massive the circumplanetary disk must be?
Yeah, I have seen the Band 9 data, and we have made predictions. And basically, they suggest that with the integration time of that Band 9 data, you may not detect it, hence why we want deeper Band 9. But I would love to discuss this afterwards.
Sounds good.
Great.
Looking forward.
Another good match. Okay, thanks again, Iain, for this wonderful detection. And we move to the last talk about the eDisk program by Yusuke Aso.
Good afternoon, everyone. My name is Yusuke Aso. It's my really great pleasure that I can share the results of our eDisk program on behalf of the team members. The eDisk team presented 16 posters in PP7, so still I hope you to enjoy these posters through the Mattermost, as well as this talk. No, not working. Oh, okay. Then I put this figure as an introduction. And as you have already seen and heard many, many times, even in the PP7, the cluster disk shows the various kinds of substructures in their disks. So like a ring, gap, and spirals. And these substructures are considered to be a sign of planet formation. So this result naturally triggers next questions. When do the planet formation start? When does the disk substructures start form? In order to answer these questions, we have carried out the ALMA large program, eDisk. The eDisk program has two main scientific objectives as listed here. One scientific objective is to search for disk substructures in a class 0 or class 1, there are those protostellar disks. This will help us to approach the initiation of the planet formation. Then the second objective is to identify a Keplerian rotation in again class 01 protostellar disks. Then this enables us to directly estimate the central stellar mass of a protostellar system. The central stellar mass is the most fundamental parameter of a protostar, and in general, it is difficult to directly estimate the central stellar mass around the young and embedded sources. Then eDisk is led by the PI Nagayoshi Ohashi, and with two co-PIs, Jess Jorgensen and John Tobin. We have also the 17 core eyes, and more importantly, the eDisk team is inviting the 19 graduate students and postdocs as the associate members. These young members are really actively driving the scientific outcomes from the eDisk project. Yeah, the eDisk targets consist of the 12 class 0 protostars and 7 class 1 protostars. Our sample represents the protostars in nearby star-forming regions. This figure shows the updated bolometric temperature and bolometric luminosity of our eDisk sample. As you can see, both of these parameters are distributed in a wide range. So this means that our sample is not biased with respect to the temperature or luminosity. Here I put a summary of the observational settings. Then here I'd like to emphasize the angular resolution. The angular resolutions for the continuum observation is 0.04 arcsecond, or 7 AU at a typical distance. The angular resolution for the line observation is also as high as 0.1 arcsecond, or 14 AU. In addition, the velocity resolution is also high enough to investigate the kinematics around the protostars using some key molecular lines such as C19O. Then let's see the result. This figure shows the gallery of the continuum emission of our eDisk sample. Then each panel has each linear scale, and the scale bar shows the 20 AU lengths. So you can fairly compare these panels. Then, as you can see, the continuum emission traces a disk-like structure with a large diversity in the size. And some of them also shows peak brightness temperature higher than 100 Kelvin. This kind of high brightness temperature cannot be explained only by the heating by the central star. So this may suggest some additional heating mechanism by the disk itself. Then, additionally, the 4 of our target turned to be binaries, even though we originally aimed to focus on the single protostars. Then here, I put a zoom-in version so that we can see the emission structures in more detail. Then as you can see, this figure tells us 2 main results. The first one is only a few of a sample shows distinctive substructures. So Dominique, hi, sorry, but this may be against your expectation, but still, this must be exciting. And another, then here, these 2 sources shows the relatively clear disk substructures, but others are not really. Then the second result is the brightness asymmetry along the disk minor axis on these modern half samples. Then these 2 points are clearly different from cluster disks, as we saw in the D-sharp sample. Oh yeah, here you can see the brightness asymmetry along the minor axis. Then here I compare the eDisk result on the left side, and the right side shows the D-sharp samples. Yeah, so this slide clearly shows these two samples are clearly different. Then from here, I'd like to focus on each result in a bit more detail. And this figure shows the ring-like structure. So this is relatively clear disk substructure found in eDisk observations. Then this image shows the ring at a radius of 50 or 60 AU. Then in addition to this image, we also analyzed the emission structure on the visibility domain. Then we confirmed that this dip in the visibility profile corresponds to the ring at a radius of 50 or 60 AU, as expected from this image. Then this is an example of the asymmetry along the disk minor axis. So you can see the peak position is slightly shifted toward the eastern side from the global center. And this result can be interpreted as a result from the geometrically and optically thick disk as shown in this schematic view. When we see the near side in this kind of situation, we see the cooler surface of a disk on the near side, while we see the warmer surface on the far side of the disk. Then this causes brightness asymmetry along the disk minor axis. Then this kind of flared disk structure suggests the grains are not settled down yet on the mid-plane at this class 1 stage. Then actually this effect is also confirmed by a flared disk model, including radiative transfer calculation by our team. Here I put the example of the molecular line result. This figure shows the C1802221, the distribution and the velocities. This figure clearly shows the velocity gradient along this disk major axis, suggesting some kind of rotation. So we analyzed the kinematics in more detail using this position velocity diagram. X-axis is position, y-axis is positional x-axis velocity. The y-axis is positional offset from the center along this axis. Then we determined this point and fitted with a power law function and have succeeded to identify the Keplerian rotation in this protostellar disk. Here, I'd like to emphasize again that the identification of the Keplerian disk enables us to directly estimate the central stellar mass. Then the lastly, I show the current publication status of the eDisk team. We are submitting the first look papers. And by the way, one of our first look paper has been accepted in this morning. Yeah, thank you. And following these first look papers, we are also working hard for the second generation papers to discuss the entire sample more systematically, including specific topics like outflow chemistry or magnetic field. Then here I put a summary and welcome the questions. That's all. Thank you for your listening.
Thank you very much. The floor is open for questions. Yes, please.
Okay, so the asymmetries is really convincing that it's optically thick. How does your results change what we've thought of for traditional mass estimates for the dust mass and the disk? How far off have we been?
The eDisk's result shows the continuum emission at the 1.3 millimeter they are mostly relatively optically thick. So this, may affect the dust mass calculation definitely. We have not yet evaluated systematically, but we will do the comparison using the latitude transfer calculations.
Okay,
in the
great.
future.
I look forward to it.
Okay, we move to the right, please.
Yeah, John Carpenter, Joint ALMA Observatory. A lot of in your continuum gallery, a lot of the disks seem to be edge-on more than, could there possibly not actually be class, or at least, could they be misclassified as class 0 and class 1 systems?
It's a good question, and that is definitely what we should check. So we aim to estimate the central stellar mass using the line observations, and also we know the barometric luminosity. So in the second generation paper, we are planning to estimate kind of age of each protostars, and so using these values, we may calibrate the classical classification, class 0 or 1.
Thanks.
Okay, one more question here.
Philippe André, Paris-Saclay. Wonderful results, thank you. Do you have any estimates for the optical depth of the millimeter emission that you are detecting in these young objects compared to what is observed in class 2 objects?
Optical depth, yes. So, well, it's definitely more optically thicker than the class 2 disks. But we have not yet estimated the accurate value.
Okay, something to come. So, very last question on the right.
Sylvie Cabri, Observatoire de Paris. Thanks for these beautiful results. I was wondering if you have, do you see a difference between the size of the disks in the continuum and in the CO, meaning that you already have radial drift, or is it an earlier stage and the sizes are more comparable in the two tracers?
Well, we identify the gas disk, but it's not only from the size of the gas emission, but we measure the rotational velocity and define the Keplerian disk radius. So, so far we don't say either is significantly larger. Some sources, the disk radius derived from the Keplerian analysis is same as the continuum size.
Okay, so that's consistent with earlier stages where it hasn't drifted in much. Thank you very much.
Okay, let's thank Yusuke Aso again for a wonderful talk.